Hello everyone and welcome back. Today we are going to solve this question. There's a ring of mass m and radius r and it is released on a sufficiently rough surface with initial linear velocity of v naught and angular velocity of omega naught such that v naught is more than r omega naught. So let us see what they mean by this thing. Alright, so we'll make the ring and this is our surface. It is touching the surface. So yeah. So I gave it an angular velocity of omega naught and initial linear velocity of v naught, and we have that, yeah, the radius is r, mass is m. We have that v naught is greater than r omega naught. What does this mean? So we know that the velocity of this point P, point of contact, is going to be the radius of the object times the angular velocity. So Vp is going to be r omega naught. So this point will have a velocity of minus r omega naught I cap. The minus is representing that it's towards the left. So Vp is like this, minus r omega naught I cap, and V, velocity of center of mass, is v naught I cap. So the net velocity of this point is towards the right. So net velocity is towards I cap. So what does this mean? This means that there is forward slipping. The ring is slipping in the forward direction on the floor. Alright, now we have this info. Let us see what we can do about it. So the ring is here and it is slipping v naught and omega naught, and it is forward slipping. If it is forward slipping, because it is slipping on the ground, we know that kinetic friction is going to act. So we are going to use kinetic friction. It's not static friction. So which is always equal to mu mg. If mg is the normal reaction, strictly speaking, this is going to be mu times normal reaction force, but here mg is equal to n, so we'll just write mu mg. So let us make the force diagram of the ring. What are all the forces acting on it? Then we'll try to solve it. So let us make the force diagram. So it has mg acting downwards and normal reaction acting upwards. Alright, it's in vertical equilibrium. It has this friction force, let's put it as acting backwards. So yeah, these are the axes. So we can clearly see that it's in vertical equilibrium, so n equal to mg. So but horizontally there's a net force towards minus I cap, so let us make that. So we know that frictional force equal to mu mg. So yeah, there's a force towards minus I cap, but what's the acceleration of it? So we know that acceleration equal to force by mass. So here force is equal to mu mg, so acceleration due to friction is going to be mu g. Alright, this is what we have. Now let us try to write the velocity of the linear velocity of this ring as a function of time. So we know that v is equal to u plus at from the equation of kinematics. So here what is u? So u is just our v naught, that is the initial velocity. And what is a? A is going to be minus mu g, because it's acting opposite to the direction of v naught. It is going to be represented by a negative sign, and t is t. So let us write v as a function of time. V as a function of time is v naught minus mu g t. Let us highlight this. So this is important. We'll need it in the future in this question. Alright. Now let us write the torque equation. So mg is going to act at the center of mass of the ring. Normal reaction will also do the same thing. So let us write the torque equation about the center of mass of this. The radius of the ring is r. So about the center of mass, torque due to normal reaction force is 0, and torque due to mg is also equal to 0, since they pass through the point about which you are calculating the torque. So there is only one force which is giving torque, and that is friction. We have our initial omega and which is clockwise, and even friction is providing clockwise torque. So yeah, what's the torque given by friction? It's just going to be force times the perpendicular distance. What is friction in this case? It's mu mg. So torque due to friction is going to be mu mg r. Alright. So even this torque is going to provide some angular acceleration. What will that be? We know that torque is equal to moment of inertia times angular acceleration. So we get angular acceleration is equal to torque by moment of inertia. So what is the angular acceleration? So the torque is mu mgr, and moment of inertia of a ring is given by mr square. So alpha is going to be m and m cancel, r and r square, one of the r's get cancelled. So we have alpha is equal to mu g by r. That's our alpha. Now we know, let us write the angular velocity of this ring as a function of time. So yeah, the angular velocity is in clockwise direction. The torque is also in clockwise direction, mu mgr, that's also in clockwise direction. So the angular acceleration is going to increase the angular velocity. So alpha is going to be positive. So we have omega naught plus alpha t. What did we get as alpha? We got alpha as mu g by r, mu g by r, mu g by r into t. So this is omega. This is our angular velocity of the ring as a function of time. What are we asked to find, by the way? The question asked us how long will it take for the ring to achieve pure rolling. Now let us see what pure rolling means. So pure rolling means velocity of the center of mass is going to be equal to the angular velocity times the radius. So this is the condition for pure rolling. Now how are we going to do it? We know velocity as a function of time, and we know angular velocity as a function of time. We know both of these. So let us try to form an equation like this. So let us express velocity as a function of time should be equal to radius times omega as a function of time, and we'll solve for t. So we have, let us go and see what velocity as a function of time was. V naught minus mu gt. Okay. So we have V naught minus mu gt is equal to now r times angular velocity as a function of time. That is going to be omega naught plus mu gt by r. Okay. Omega naught plus mu gt by r. Now we are going to try to solve for the variable t. Let us just do some algebra. Let us expand this bracket. V naught minus mu gt is equal to r omega naught plus, and if I multiply r with the second term in here, there is an r in the numerator and 1 in the denominator, so it will get cancelled. So we have plus mu gt. So which gives us, taking mu gt to one side and r omega this way, we get V naught minus r omega naught is equal to 2 mu gt. Now dividing both sides with 2 mu g, we get t is equal to V naught minus r omega naught by 2 mu g. So this is the answer which we have been wanting. So this is the time the ring will take after being released to achieve pure rolling. And once it achieves pure rolling, the friction, once it achieves pure rolling, so V naught, and this velocity of this due to the rotation is going to be r omega naught in pure rolling, and velocity of center of mass is v naught. But in pure rolling, we know that v equal to, okay, it's not going to be omega naught, it's just going to be some v and some omega. So v equal to r omega, right? So the same velocity is minus I cap and same is I cap, so it gets cancelled. So we can see that this point is instantaneously at rest with the ground, with respect to the ground. Therefore, only the static friction is going to act, and as it is at rest instantaneously, the friction won't do any work. So once it reaches pure rolling, it will continue on pure rolling forever in an ideal case. Okay, now we did this for a ring. Now let us try doing it for any rolling object. Let us generalize this case. So we get, let us take the moment of inertia to be k times mr square and mass to be m and radius to be r. These are the parameters of our object. Any rolling object will have all these three parameters. Alright, so let us quickly, for visualization we'll just make it as a round, but I'm not telling that it's a sphere or something. Just for visual purpose, I just made some diagram. So yeah, friction will act backwards. So what is the force? So let us write velocity as a function of time again, v naught, and it has omega naught again. So velocity as a function of time is v, so acceleration due to friction is mu g minus mu g, so is equal to v naught minus mu g t. This is the same, and now let us write the torque equation, and let us write the angular velocity as a function of time. So here we can see that the angular velocity and the torque due to friction are in the same direction, so the angular acceleration is going to be positive. So we have torque due to friction as mu mgr and moment of inertia as kmr square. So what will the angular acceleration be? Angular acceleration is equal to mu, I'll write the formula, is equal to torque by moment of inertia, which will be mu mgr by kmr square. It is going to be the r square and the r cancel, we are left with 1r, m and m cancel, we get mu g by kr. That's the angular acceleration. So angular velocity as a function of time will be omega naught plus mu g by kr alpha t, right? So mu g t by kr. Okay, now let us, okay, I'll put the background as black. Now let us make the equation. V of as a function of time should be equal to omega as a function of time times the radius. So we have v naught minus mu gt is equal to r times omega naught plus, what was the angular acceleration, mu gt by kr, mu gt by kr. Yeah, this is what we have. Okay, let's just expand this. V naught minus mu gt is equal to r omega naught plus mu gt by k. The r in the denominator and numerator get cancelled. Now let us get this to this side of the equation and r omega naught that way. So we have v naught minus r omega naught is equal to mu gt into 1, I'll write the step so that people don't get confused, plus mu gt by k, and then we are finally left with v naught minus r omega naught is equal to mu gt into 1 plus 1 by k. So, and finally we get t is equal to v naught minus r omega naught by mu g to 1 plus 1 by k. Let us simplify this further, and we are finally left with T is equal to V naught minus R omega naught times K by mu G into 1 plus K. That's what we are finally left with. Now this is, as we just assumed it for a general rolling object, this formula right over here. Now let us just verify to see if we did it right. We know, let us compare it with the answer we got for the ring. We know that for a ring, moment of inertia is going to be mr square. So K is just going to be 1. So now let us put K into this formula for a ring. I'll just write for a ring. For a ring, yeah. Let us put K equal to 1. So what do we get? T is equal to V naught minus R omega naught times 1 by mu G into 1 plus K. That's 2. So yeah, we got V naught minus R omega naught by 2 mu G. Now let us go back and see what we have solved for the ring. That's the exact same thing. So this formula which we have derived at the end, it's a universal formula which is applicable for any rolling object. So you just have to find the value of K and substitute it in this formula and you will get the answer. So yeah, this is a universal formula and people can use it for any object, any rolling object, and we are done.